Hi, this is Rick Merritt from EETimes. We're here today with Mike Muller from ARM, the Chief Technology Officer of ARM, who gave the keynote speech, one of the keynote speeches at the ISSCC conference this morning. So thanks for taking some time to come over to the office, Mike.
Thank you for inviting me.
Glad to see you. So one of the things you talked about in your keynote was that we're seeing the benefits of scaling reduced now in the current generations as we get to 65 and 45 nanometer. What does that mean for the chip designer?
Yeah, I think one of the things I was saying is, some of the only good news in process technology is that transistor scaling continues and they get smaller and smaller and you can fit more and more on the chip. But if you look at power and performance, going from 180 to 130, 130 to 90, you used to get a higher performance, and if you use that higher performance, you still got a lower power. As you go from 90 to 65 and 65 to 45, that has changed fundamentally, and now you have to choose your process. Do you want a high performance process? Do you want a low power process? And even in the low power process, if you use the maximum frequency that the process gives you, the power goes up. So you can no longer take a design and scale it, add more functionality, and expect to get a better product that's cheaper with more in it. And that fundamentally changes the way that people actually need to approach design. And what I was saying is, if you're not in a multidisciplinary team looking at the software, the operating system, the architecture of your system, the microarchitecture of the components, and how you've actually built the libraries, you can't join everything together to get the savings you need in the power performance trade-off to build optimal systems. And if you just focus on implementing one of those components, you'll be doing a local optimization. You won't actually be getting the best product you can.
What about just the power part of that equation? As so much of the system design is moving to mobile and wireless design, what do you see as sort of the next big step for power management just at the industry level?
Well, I mean, the process again is sort of working against people because, again, over time voltages have gone down with each generation, and voltage is one of the key ways of reducing power in a design. It pops up in static and dynamic active leakage power, and the only thing you can do about that is to reduce voltage. But the process guys have had fundamental problems because as you lower the voltage, it's hard to build bit cells that yield reliably. So one of the things we've been looking at in the design techniques are what can you do to push some of the margin that is out there in the design. Because when you look at things, you've got a library, a little bit of margin in it. You've got some EDA tools, they add a little bit of margin. There's the fundamental SPICE models from the foundry, they add a little bit of margin. When you add all of those margins together, you're actually losing frequency or power or yield. And the only way to address that is to actually find out fundamentally what does your silicon do. Now, if you have a market that can sustain high margin for some components where you can charge extra, then maybe you can just take that distribution and make money out of it. But in any real true high volume market, that's not there. You have to yield across the spectrum. So people need to find techniques for how you take margin out. And in the cell phone, in the analog world, people have been doing this all the time. Your cell phone doesn't run full power. The radio backs off until the error rate is just about right, and then copes with those errors and preserves your battery life. But in the digital domain, everyone's used to saying, the transistors work, I never make mistakes. And actually, we think there are design techniques that mean you have to start backing off from that and going, occasionally, my circuit will go wrong, and I have to detect those errors, correct them, and move on. And as long as the detection and correction of those errors takes less power, you're better off, even though you've now got a system that's fundamentally unreliable.
So there's really some new dynamics coming up here in design being more of a system level process and being more of a almost sort of analog kind of techniques.
Yeah, and that's where if you're not open to what your fundamental process and libraries are doing in the analog domain, that ripples all the way through to the operating system, because you need to have software that actually can manage all of these different power modes and actually deploy them in a product in a usable way. So you can't just look at, oh, I'll do some really neat circuit techniques and then hope that the software guys might find a way of using it. You have to design the two together from the very beginning.
All right, last question. One of the things that comes out of this ISSCC meeting is the disclosure of Silverthorne, the x86 processor Intel has done to get the x86 architecture down below a watt for some workloads. So from ARM's perspective, what's your response to seeing the x86 get into this kind of low power space?
Sure, as you said, for some workloads, under some conditions, for some chips. So I think we'll have to wait to see what the real data is. And, you know, it's interesting, they're trying to come down into the mobile market. You know, kind of the mid devices, mobile internet device is currently relatively small, few million units. It may grow over the next few years to 2010 to maybe, I don't know, 20, 50 million units. But at the same time as that, the category below that is going to grow to 400 million units, and that's kind of web-enabled smartphones, and that's more web-enabled smartphones than PCs ship. And it's not just about the processor. You actually have to deliver complete SoCs with all of the radio, all of the I/O components in single chips, and that's what you have to bring in at a few hundred milliwatts maximum performance, not just the processor component. And you need to take the whole ecosystem that goes around that. You have a chip, it may be quite good, but you know, can you run Windows Mobile? Can you run Symbian? Can you run Mac OS X? Can you run Google Android? There's a whole plethora of third-party systems and components that are part of the mobile world that we come from that aren't in the PC world. And as the internet changes from something that's browsed more on the phone than it is on the PC, those relationships that come from the world that ARM comes from actually become more and more important.
Well, thanks for the great feedback, Mike. I really appreciate you coming out today.
Okay, thank you.
This is Rick Merritt from EETimes. Thanks for tuning in.